This lesson is on the scalar equation of a plane. Our learning goals are to find the scalar equation of a plane in 3 space using given information, determining whether or not a point lies in a plane, learning to determine whether 2 planes given in vector form are coincident or not. We're learning to decide whether 2 planes given in scalar form are parallel and distinct, coincident, or neither, and also learning to find the x, y, and z intercepts of a plane, and also learning to find the shortest distance from a point to a plane. So a plane has a unique normal and therefore has a scalar equation. Okay, I'm going to do a little whiteboard here with you. So if we think of this as our plane, we need 2 direction vectors. There's one, we can call that M1, and here's the second direction vector, M2. And if I do the cross product of those 2 direction vectors, I'm going to get a third vector that is normal to the plane. Okay, so a plane does have a unique normal, a direction that is perpendicular to the two directions that define the plane in the vector equation. So that's kind of what I've got drawn here. So a plane has a unique normal and therefore it has a scalar equation of the form ax plus by plus dz plus d is 0. It can be found using qp dot n equals 0, where q is a point we know in the plane, p is our generic point x, y, z, and n is a normal to the plane. And then the normal to the plane can be found by finding the cross product of the 2 direction vectors. Okay, so this is kind of the setup I have here, where we've got our known point in the plane, our generic point, these are both on the plane, and we've found the normal already. And the normal is A, B, C. Which is also cool too, remembering that A, B, and C, in this case, represent the normal to the plane. Okay, so we'll start with an example. The plane has this vector equation. Determine the scalar equation of the plane. So just by looking at the vector equation of the plane, we know that this can be our point Q. So we know Q, the point we know for sure is on the plane is -2, 5, and 3. An arbitrary point on our plane can be x, y, z, but we also need the normal of the plane. And to do that, we're first going to find M1 cross M2, and that will be in the direction of the normal. We might want to take a smaller scalar multiple if there is one. So here's my first direction vector, 2, 4, 1, and my second one is 1, 4, 2, and I'm going to cross them. So back to using the cross product here. So that's going to give me 8 minus 4, which is 4, 1 minus 4, which is -3, and 8 minus 4, which is 4 again. And there isn't a smaller scalar multiple, so we'll just use that as our normal. And then we'll go into our QP vector, dotted with the normal has to equal 0. Again, if you look at this picture up here, it's because they're at 90 degrees to each other, because QP is in the plane. So if we have our plane here, P is an arbitrary point where we don't know it. Q is a point we do know. In our case, it happened to be -2, 5, 3. And then we can make a vector by joining Q and P. So there's our QP vector. And if we dot it with a normal to the plane, which we know is at 90 degrees to it, we know that their dot product is going to be 0. So that's why we can say this statement and it's true. So QP is P minus Q, so x minus -2 is x plus 2. y minus 5, z minus 3, dotted with our normal, 4, negative 3, 4 has to equal 0. Dot is multiply and add. Remember, we're distributing here, so we're doing x plus 2 times 4, which gives us 4x plus 8. Negative 3 times y minus 5 is negative 3y plus 15. And 4 times z minus 3 is 4z minus 12. And then we'll collect our constants here. So 4x minus 3y plus 4z. And then 8 and 15 is 23, minus 12 is 11, so plus 11 equals 0. So that's the scalar equation of the plane. And notice that the normal here, 4, negative 3, 4, we can see as the coefficients of x, y, and z in our scalar equation of the plane. Okay, so determine the scalar equation of the plane passing through those 3 points. So from those 3 points, we can make 2 direction vectors. So first I'm going to make the vector AB and use that or a scalar multiple of it as my first direction vector. So negative 1, take away negative 1 is 0. 2 minus 3 is negative 1. Negative 1 minus negative 2 is positive 1. So I'll let that be my M1. And then I'll also find vector AC, so C minus A. 4 subtract negative 1 is 5. 1 subtract 3 is negative 2. Negative 2 subtract negative 2 is 0. So that's going to be my M2. And then I'm going to find what M1 cross M2 is. And either that or a scalar multiple of it will be our normal. So we're doing the cross product. Starting here, downward minus upward. So that's going to be 0, subtract negative 2, which is positive 2. 5, subtract 0. And 0, subtract negative 5, which is positive 5. So that's going to be our normal 2, 5, 5. So we've got our Q is a known point. I can use, instead of using Q, I can use A if I want to. P is my general point that lies in the plane, and my normal is 2, 5, 5. So instead of QP dot n equals 0, I can say AP, same thing, dotted with n equals 0. A is just a known point on the plane. So in this case, AP is P minus A, so it's going to be x plus 1, y minus 3, z plus 2, dotted with the normal, 2, 5, 5 equals 0. Dot is multiply and add. Remember to distribute, so we're going to get 2x plus 2 plus 5y minus 15 plus 5z plus 10 equals 0. And collecting our constant terms, so I'm going to get negative 13 plus 10 is negative 3. So our scalar equation is going to be 2x plus 5y plus 5z minus 3 equals 0. Our third question here, find the scalar equation of the plane containing 2 parallel lines. Okay, so if I do a little sketch here, I'll do it over at the side here. So again, if we have 2 parallel lines, we're given one direction, and we have to find a point-to-point vector to get our second direction. So I'll call this point Q1, for instance, and this point Q2. And from this symmetric equation, I know that Q1, so a point I know on this plane, if I exaggerate the symmetric form here, would be 0, 4, 1. And the direction of this line, given in symmetric form, would be, the direction vector, sorry, would be 3, negative 2, 1. And then this plane, or sorry, line, sorry, this line given in symmetric form has a point Q2, and that point is 3, 0, 1, and the direction vector of this second line is 3, negative 2, 1. Remember when you're dealing with symmetric forms to check and make sure that they are in fact in symmetric form, x, y, and z have to be first and not negative, all right? And if they are, then you have to change them by multiplying top and bottom by negative 1. Okay, so here we have to find, sorry, I should have called this is M1 and M2 are the same, so I should have called this one M1 as well. So from these two lines, we are only given one direction because these are parallel lines. So our second direction comes from making this vector. Vector Q1, Q2. So let's make vector Q1, Q2. So it's going to be Q2 minus Q1. So 3, negative 4, 0. And we'll let that be our M2. So we have two different directions now. Okay, so these are equal again because the lines are parallel. And then we made a different direction by finding the direction vector from Q1 to Q2. So now we can find the cross product of M1 and M2, which will be in the direction of our normal to the plane. So I'm going to do that over here. So 3, doing the cross product. So that's going to be 0 subtract negative 4, which is 4. 3 subtract 0, which is 3. Negative 12 subtract negative 6 is going to be negative 6. And I can take a smaller scalar multiple there, so I could have my normal be divide everything. Oh no, I can't actually. So that is going to be my normal. So I've got to choose a point, so I'll choose Q1 because I know it's in my plane. An arbitrary point, x, y, z, and my normal, we just found, is going to be 4, 3, negative 6. And then I'm going to set up Q1 P vector dotted with n vector equals 0 to get our scalar equation. So P minus Q1 is going to be x minus 0, which is just x, y minus 4, z minus 1, dotted with the normal, equals 0. So if I multiply and add, I'm going to get 4x plus 3y minus 12 minus 6z plus 6, be careful when you distribute there, equals 0. 4x plus 3y minus 6z minus 12 plus 6 is minus 6 equals 0 is the scalar equation of the plane containing the parallel lines. Question 4, find the equation of the plane that is parallel to the plane. So parallel to another plane, in your mind you're going to say parallel to another plane means same normal as the other plane. So parallel planes have the same normal. And by looking at this plane, 3x minus y plus 2z minus 10 equals 0, we know its normal is the coefficients of x, y, and z. So 3, negative 1, 2 is its normal. So we know that's its normal. And we're finding the equation of the plane with this normal that passes through this point here. Passes through the point A, negative 1, 0, 1. So that's like our Q, but it'll call it our A, our known point on the plane. And P is our arbitrary point, or general point on the plane. So I can make vector AP and dot it with the normal, and I'll end up with 0 because they're perpendicular. So vector AP is P minus A, so that's going to be x plus 1 y, z minus 1, dotted with 3, negative 1, 2 is equal to 0. 3x plus 3 minus y plus 2z minus 2 equals 0. Collect the constant terms here. 3 minus 2 is 1. And that's the scalar equation of the plane, parallel to this plane, but going through this point. Question 5, is the point 6, 7, 6 on this plane? And it's given in vector form. And we saw yesterday how to do this using systems of equations. But today what we're going to do is find the scalar equation of the plane. And then we just need to do a left side, right side check. It's much easier. Find scalar equation of this plane. So in order to do that, we have our two direction vectors, m1 and m2, and we're going to find their cross product. So we'll have our normal. 5, 1, negative 2, repeat the 5. So the cross product is going to be negative 8 minus 0, so negative 8. 0 minus negative 6 is positive 6. And 3 minus 20 is negative 17. And I'm just going to allow I'm going to have my normal be, because I know the coefficient of x should be positive, so I'm just going to take a scalar multiplying each by negative 1. And we know that Q, a point that we know is on the plane, is 5, 0, 4. And our general point is x, y, z. So we're going to find the scalar equation by doing QP dot n equals 0. Vector QP is going to be x minus 5, y, z minus 4, dotted with our normal 8, negative 6, 17 equals 0. And 8x minus 40 minus 6y plus 17z minus 17 times negative 4, negative 68. So 8x minus 6y plus 17z, and then we're combining negative 40 and negative 68 minus 108 equals 0. So that's our scalar equation. And now we're checking, is P676 on this plane? So we can do a left side, right side check. So on the left side, we have 8x minus 6y plus 17z minus 108. And on the right side, we have 0. And we're testing out x being 6, y being 7, and z being 6. And then we can calculate that. So that's going to be 48 minus 42 plus 17 times 6 minus 108 does equal 0. So therefore, left side equals right side. Therefore, P676 is on the plane. And a big idea that we could get from this question we just did is that a plane has an infinite number of vector equations. Vector equation is what we talked about earlier, but they only have one unique scalar equation. So question 6, are these planes and they're both given in vector form, are they coincident? Are they actually just two different ways of writing the same plane? So we can use this big idea to figure out whether this is true or not. We can find the scalar equation of each plane and see if they are the same, if they have the same scalar equation. So that could be one tactic we would take. Do they have the same scalar equation? So I'm going to kind of divide my space into two sections, because really we want to see if they have the same scalar equation. So this is plane pi 1. Pi is a short form for planes, and on this side we'll do pi 2. Now in order to have the same scalar equation, they'd have to have the same normals. If they don't have the same normals, I can stop. They aren't coincident. Okay? In order to be coincident, they would have to have the same normal. So for my first question here, to find the normal, I'll call normal 1, I'm going to do the cross product of the direction vectors. So I'm going to do that on some scrap paper. Sorry, just give me a second to find some. Okay. So here's my direction vector, 2, 0, -1, repeat the 2. And my next direction vector, 6, 2, 0, repeat the 6. So n1 is going to be 0, subtract -2 or 2. -6, subtract 0. And 4, subtract 0. So, and I'm actually going to take a smaller scalar multiple of that. So my n1 is actually, I'm going to divide by 2 here and make it 1, -3, 2. Okay? And then I want to find my second normal, because if the two planes don't have the same normal, then they're not going to be coincident. So here's one direction vector here, 5, 3, 2, crossed with 2, 4, 5. So 15 minus 8 is 7. 4 minus 25 is -21. And 20 minus 6 is 14, which I can reduce. Everything's divisible by 7. So my n2 is 1, -3, 2. Now if we look at them, they've both got the same normal. So we would go further than that, okay? So now we're going to find the scalar equation of the first one. So we've got the normal. We've got our point Q1, our known point on the first plane, I'll call 3, 0, 2, and our point x, y, z. So we'll find Q1P vector dotted with n1 equals 0. So Q1P is going to be x minus 3, y, z minus 2, dotted with our normal, which is going to give us x minus 3 minus 3y plus 2z minus 4 equals 0, or x minus 3y plus 2z minus 7 equals 0. So similar on this side, the point we know is on our second plane, we'll call Q2, and it's the point -1, -2, 1. We'll still have our arbitrary point x, y, z, and this time we have our n2 normal. We'll find vector Q2P, dot it with n2, set it equal to 0. So Q2P is going to be x plus 1, because it's x minus -1, y plus 2, z minus 1, dotted with 1, -3, 2, equals 0. So dot x plus 1 minus 3y minus 6 plus 2z minus 2 equals 0, collect the constants. So that's going to be -5 minus 2 is -7. And look, they are in fact the same plane. So since R1 and R2 have the same scalar equations, pi1 equals pi2, the two planes equal each other, which means they are coincident. Okay, so we were given the vector equation of two different planes. Are they coincident? Our strategy was to find the scalar equation of each plane. If they have the same scalar equation, then they're the same plane, which means they're coincident. Determine whether the following two planes are coincident, parallel, and distinct, or neither. So this time we're given the scalar equations. So first we'll look at the normals, we call a normal analysis here. So n1, the normal of the first plane is 1, 3, -1. And the normal of the second plane is 2, 6, -2. So we're going to check and see if they're scalar multiples of each other. And they are, so we can see that n2 is equal to 2n1. So that means therefore parallel, they're either parallel and distinct or coincident. They're either the same or they're parallel and distinct. So what's our test? Our test is going to be whether this statement is true or not. Are the constants in the same scalar multiples as the normals? So is D2, this constant here, so this is D1, this is D2. Is D2 -8? So I'm thinking to myself, is -8 equal to 2 times D1, which is -2? And the answer is no. Okay, so when I make this statement, I go and test it, and this can be done like in your head or on the side, but then I write D2 does not equal 2D1. Therefore, the planes are parallel and distinct. So if the constants were in the same scalar multiple, then you could just like divide everything here by 2 and you'd result in getting this plane, which means they would be the same plane. If they're not, if the d values are not in the same scalar multiple as the normals, then the planes have the same normal. They're parallel to each other, but they are distinct. Okay, they're parallel but not the same plane. All right, so again, you can do that on the side, and that's how you would tell. So you always start off, whatever this statement is, you make the same statement for the d values, test it, and either keep it equal, in which case you'd have coincident planes, or you cross off the equal sign if it's not true. Okay, question 8. Find the x, y, and z intercepts of this plane and sketch a portion of it. Okay, so to find the x-intercept of a plane, it occurs when both y and z are 0. Okay, so you can see if I'm going to put something on the x-axis here, it's going to occur when both y and z are 0. Okay, so it's pretty easy to find. If you can mentally set y and z to 0 here, and you'd be left with 3x minus 12 equals 0. And you can solve for your x-intercept. Add 12 to both sides. Divide both sides by 3. And you get x equals 4, which means it's the point 4, 0, 0 is the x-intercept of the plane. And there I plotted it there. Positive x is out. To get the y-intercept of the plane, that's when x and z are both 0. So I can mentally set them equal to 0. 3 times 0 is 0 here. 2 times 0 is 0. So I'd be left with 4y minus 12 equals 0. Add 12 to both sides. Divide by 4. And you get y is 3. Which corresponds to the point 0, 3, 0. So positive 3 there. So there's my y-intercept on the y-axis in the positive y direction. And then my z-intercept is when x equals y equals 0. So I would be left with 2z minus 12 equals 0. Where z is 6, positive 6. So that's the point 0, 0, 6. 1, 2, 3, 4, 5, 6. There, extended it so we'd have room to draw it on. And then to sketch a portion of the plane, what we're going to do is sketch a triangular portion. So we're going to join the x-intercepts together to form kind of a triangle. And then usually you just shade it in with hash marks, one direction and then the other direction. And you've sketched a portion of the plane. Okay, so they're pretty straightforward to find. All right, the distance from a point to a plane. Okay, so here we are with our projections again. It's the scalar projection of QP onto N. So Q here is a known point in the plane. P is the point we're trying to find the shortest distance from. Point we are finding distance from. N, this direction here, direction is the normal to the plane. We know that. Normal to the plane. And our light source always comes in perpendicular to our normal here. So here's our light source, because this is our normal. Do my normal in a different highlighter here. So this is my normal direction. Our light source is perpendicular. This is my vector QP. Just go over it here. So there's my vector QP. So if I'm shining a light, the shadow of QP on the normal is going to give us this vector here. From here in the pink up to here. And that the magnitude of that projection is going to be the distance, the shortest distance from this point to this plane. Okay? So the distance is the magnitude of the projection, or the scalar projection of QP onto the normal of the plane. And we know that that breaks down into the magnitude of QP dotted with N over the magnitude of N, because that's the formula for the scalar projection. Okay? Remembering what all these are, P will be given. It'll be the point we're trying to find the distance from. Q will be a point we know on the plane. Similarly to when we did this in two space, the distance between a point and a line in two space, we often chose an X or Y intercept. In this case, we might choose an X, Y, or Z intercept of our plane as our Q. Okay? The distance is what we're finding, and the normal, if we're given the scalar equation of the plane, we will know the normal of the plane. So here's an example. Determine the shortest distance from the point A, 1, 2, negative 4 to the plane 3x minus 4y plus 8z minus 12 equals 0. So we've got this situation here where this point is like our point A here. Okay, so we're trying to find how far this point is from this plane here. So our point P, if we want, we can just rename this so it's not confusing to follow. So our point P that we're finding the distance from is point A, really, 1, 2, and negative 4. Point Q, a point we know to be on this plane. Okay, so we can look and see, oh, it's easy to find the x-intercept. So let's get the x-intercept of the plane. So we would set y and z equal to 0, and we would get 3x minus 12 equals 0, or x is 4, meaning the point 4, 0, 0 is a point we know lies on this plane. So that's going to be our Q, our known point on the plane we found was our x-intercept, 4, 0, 0. And the normal to the plane is our A, B, and C, including signs here. So our normal is going to be 3, negative 4, 8. And our formula is that the distance, the shortest distance from the point to the plane is the magnitude of the projection of QP onto the normal, which is the magnitude of the projection. So QP is going to be 3, negative 2, 4. Oh, no, I should just go to the formula now. So that's QP dotted with n over the magnitude of n. And now let's find QP. So QP is P minus Q. So it's going to be 1 minus 4, negative 3. 2 minus 0 is 2. Negative 4 minus 0 is negative 4. Dotted with our normal, 3, negative 4, 8. Over the magnitude of the normal, square root of 3 squared plus 4 squared plus 8 squared. So the distance is going to be, so when I do the dot product here, I'm going to get negative 9 minus 8 minus 32 over the square root of, it's going to be square root of 89. So our distance is going to be, so the magnitude of negative 49 over the square root of 89. So this means absolute value of negative 49, which is positive 49, over the square root of 89. That's exact, but we usually like to figure it out approximately. So 49 divided by the square root of 89 is approximately 5.2 grid units, would be the shortest distance from the point to the plane. So again, how did we do that? We had our point that we're finding the distance from. We found the x-intercept because it was easy to find. Sometimes it won't be, and the y or the z-intercept will be easier to find. So we did that over here to find our point we know on the plane, we call Q. The normal to the plane is the A, B, and C coefficients of the scalar equation. Then we use the formula, the magnitude of the projection of QP onto n, figured out vector QP. Remember, when you do dot product, you get a number. If it's a negative number, you take the absolute value of that in your numerator. In the denominator, you're finding the magnitude of a vector, so you square root the sum of the squares of the components of the vector. All right, so that's the end of our lesson.